Let's take a look at this problem. We are given natural numbers a, b, c, and d. If ab equals cd, then prove that a plus b plus c plus d is not a prime number. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. I'm going to prove this result with two approaches. The first approach is that assume the opposite, which means a plus b plus c plus d is prime number. Since we know that these four numbers are natural numbers, which means they are at least 1, so the sum is at least 4. Now from this, I'll say this is equal to p. Now given that AB equals CD, I can say AB equals C times P minus A minus B minus C. And by considering what P is congruent to C times minus A minus B minus C mod P, then the same remainder when they're divided by P. So that means it's congruent to minus AC minus BC minus C squared mod P. It's just expanding. So therefore, AB plus AC plus BC plus C squared is congruent to 0 mod P. And for this expression, we can actually factorize it. And so we know this product is congruent to 0 mod P. And since P is a prime, that means P either divides C plus A or P divides C plus B. But now we know that P is equal to A plus B plus C plus D, and they are clearly larger than each of C plus A and C plus B. So actually, at this point we have a contradiction. Because this is clearly smaller than A plus B plus C plus D, which is equal to P. So that means we have our desired result. So this is the first approach. My second approach is to start with the statement or the condition AB equals CD. From this we can say A over C equals D over B. Then I'm going to add both sides by 1. And simplifying, we can have A plus C over C, combining 1 and a fraction. Doing the same at the right, we have D plus B over B. So then A plus C equals D plus B multiplied by C over B. Then we can add both sides by B plus D. So at the left we have A plus B plus C plus D, while for the right we have D plus B times C over B plus D plus B. While for the right we can take out the common factor, and so we have C over B plus 1 inside the bracket. Now we can see that this sum equals D plus B times C plus B over B. So now we can analyze this fraction. Just if, that, for example, B itself divides either D plus B or C plus B, since we know that D and C are positive, so that means the fraction, then either the fraction D plus B over B is at least 2, or it's the other fraction that is at least 2. Then I can write this sum as, say, this integer, which is now just phrased as a fraction, but we know it's an integer, multiplied by c plus b, and both are at least 2, so not prime. Or the other way around, again not prime, using a similar argument. Or somehow b is a composite number, and we can split b into product of two numbers, and each divides one of d plus b and the other divides c plus b. Now from this it's even more obvious that each quotient is at least 2. Then we can write this fraction as p divides d plus b, and then q divides c plus b. Then d plus b over b times c plus b over q, and each fraction is an integer that's at least 2. Again, not prime. So then we have also proved the claim, but in another approach. Please feel free to share ideas in the comments. Thank you for watching. See you next time.